Uh, so let's start. With this presentation, I'm going to try to offer a short very personal interpretation of GIS applications in archaeology. Please don't get offended if, if this doesn't coincide with your own. Some of us are older here. I also wanted to discuss current and new approaches to the use of geospatial technologies in archaeology. And I will also try to propose ways in which the discipline might evolve in the next years, using my own research as an example. I'm using my own research because it's the only one I understand well, but there's a lot of work there that is of very high quality, but it's much easier. I have already presentations, I can, it's practical. And then I will try to reach some general conclusions that we can discuss. So, GIS during the 70s and 80s, it was highly innovative for the time. I mean, highly innovative because it was the first time that it was done. The applications were highly specialized, many of them involving their own GIS-based software. Okay, and they were not doing complex analysis. They mainly were things like database organization linked with spatial shapes, some basic representation of topographies, basic stuff, but very practical. Okay, that was difficult to do by hand. And that marked the beginning of the hype curve with GIS. Okay, from this moment on, applications started to multiply. Oops, sorry. Then during the 90s, 2000s, it's rough. Okay, and there's lots of small detail here, but I would say this marks the peak of the inflated expectations of the hype curve. There was certain kind of fear of missing out. Okay, lots of people joining the fashion. I mean, do you remember there was this subdiscipline named CAD? I mean, at some point, GIS and CAD were presented in the CAA as kind of subdisciplines. Thankfully, CAD passed to mere software, but this was not the case for GIS, no? And during this period, we have in the CAA became enormous. And there was, I mean, it was a period in which you were going to the CAA and you would only see lots of view sheets, less code roof analysis, shaded relief models everywhere. It was a bit too much without that much analysis behind it. And many of the things presented you could do by hand, basically. So GIS during this period received lots of criticism from the postprocessual community. And it's a pity because there were lots of GIS experts, most notably Mark Gillings, that tried to approach to have some post-processual approaches using GIS, mostly with visibility, but with other types of approaches thought to reach post-processual conclusions that were not accepted. I remember quite hard criticisms from post-processual popes to GIS. So yeah, that marked a kind of disillusion. I mean, people got a bit frustrated. So during the 2010 and the next few years, we have important advances in remote sensing. I mean, mostly because early approaches to remote sensing were mostly reduced to photo interpretation. And there were some exceptions, of course, but lots of remote sensing was trying to find the structures or sites from satellite and aerial images. There was also lots of advance in 3D modeling, and GIS lagged a bit behind because there was scarce implementation of new algorithms. For example, still today, for the calculation of cost movement, we have only 8 directions in the dominant GIS software, which is incredible. I mean, there's been 20 years that the night move algorithm was implemented in GRASS. So there's also lots of problems with the implementation of parallelization. And, I mean, there has been some availability of cloud computing resources, but this This is probably due to the fact that those are very easy to commercialize, okay? But not really, I mean, lots of software still today does not use the multiple cores our computers have, okay? Or computers have in general. There's also very scarce implementation of GPU computing, which is a pity for very intensive processes like the development of accumulated surfaces. This would really simplify the work, but well, they are simply not implemented. Although there are publications that with code that show how to do that, but there has not been advances on this, and and most GIS softwares today incorporate coding consoles, but they are scarcely used in archaeology during the 2010s. Okay, so this I would say marked the depression of the hype curve. Yeah. So where do we stand now? There's an apparent fragmentation of the discipline. We have people doing. They say they do GIS, which includes CAD, 3D, and remote sensing today. I mean, the most advanced software, has vector CAD-like capacities. Today, in fact, CAD includes also 3D and GIS, so it's very difficult, and remote sensing, so it's very difficult to differentiate between these two types of software. It's more based on tradition than anything else. Remote sensing software also includes vector-based analysis and all types of raster analysis, typical also of GIS, and 3D programs include CAD and remote sensing, I mean, mostly for the collection of data. Photogrammetry also includes remote sensing. For example, many photogrammetry software includes ways to filter point clouds and acquisition of laser data. So, I mean, basically this differentiation is mostly based on tradition. It's not on a practical level, it's not like that anymore. So, I mean, the practical application, not at all, I would say. So, I mean, I guess we need to embrace this divergence and see it as a way to move GIS science to integrate all this in a single discipline, okay? Also, today, specialization seems more pronounced. You have people that are more specialized on remote sensing or machine learning or 3D analysis, because it's getting very difficult to be able to control everything. You need to study a lot to keep on top, and techniques are becoming quite complex. So it's the typical guy who searches for everything, and is doing the GIS, but also the remote sensing and the topography. This is hopefully finishing. So. So why all this? Why all the fuss with computational or geospatial approaches? Yeah, during the last few years, there's an increase again. Not of GIS, but perhaps computational based approaches, which include a lot of geospatial approaches. And this is probably due to the availability of much more data, including lots of public geographic data. I mean, with the Sentinel missions and the Copernicus science and the Inspire initiative. Wow, now we have access to data that previously we had to digitize by hand. I mean, probably most of you don't remember or didn't have to digitize by hand with a tablet a topographic map. It's a nightmare. So there's also new methods for data collection and sensors, drone, LiDAR, new scanner types. I mean, you have now structured light scanners are becoming very efficient. New methods for data analysis, particularly agent-based modeling, machine learning, other types of statistical modeling, in which coding plays an important role. There's also a higher availability and more powerful computation with cloud computing, new GPUs, new frames like CUDAs and TensorFlow for the analysis of data. There's also more open data with emphasis of fair data and data repositories, which facilitates our work and boosts the application of these approaches. And there has also been a generational change. Okay, young people are becoming very interested in this kind of approaches, and they are specializing. So that's how I would I would justify the increasing popularity of computational approaches during the last years. So what I'm going to try to do now is to go through certain types of analysis to show how today we don't do things as before, how these analyses have improved, have changed, and how they are not just GIS based, but they include lots of different stuff. Okay, I will go very fast through. Okay, so we can comment later, but I'm not going to get into detail in anything. Okay, so don't worry if you cannot read anything. I will be explaining. So I will start with root analysis. I didn't do it with viewshed analysis because it's not something I'm very interested right now in. I think with viewshed analysis we are moving very much into virtual archaeology, which really can produce. And I didn't put an example, but with Frosini Boutsikas from Kent now with a Marie Curie with us again in GIAP. We are recording Greek temples and reconstructing them and putting them in virtual environments with horizon lines and with the sky, simulations of the sky to try to simulate. So I think this is much more interesting than the old viewsheets. And yeah, with root analysis also, we are used to these lines from 2 points. Okay, I think root analysis is changing a lot. My own work on this, which I will present in the CAA next week, I think it is. So if any of you is interested, you will have a very detailed explanation of this, probably too detailed. So these are the new approaches. I think they are moving towards multi-temporal seasonal root reconstructions with data fusion using different sources, machine learning approaches, not just classification, but also regression to create new data types and to extrapolate cost. Probabilistic, they are probabilistic instead of single lines. Multi-factor, that is not just the slope, which is the most used factor, but many others. They incorporate multiple origins and destinations, stops, attractors, and they, or at least this is something we are trying to implement, but it's very costly computationally, is they have convolutional approaches that can accommodate a combination of factors. You know, for example, if it's very hot and dry, and there's no water, you will probably have to add a cost. But if there's water close, then this the hydration factor will not be so high. So you need a convolution to take into account proximity to water sources, and this is very costly computationally. Also, convolutions can accommodate things like type of transport, of change of transport, because it's not just speed or cost, but how much will an animal or a person be able to walk during a day, the distance they can cover, and you need convolutions for this. Okay, so also increase of direction, not just as implemented in most GIS packages, but at least 16. Combination of approaches, not just core surfaces, but also network analysis. I mean, the core surfaces can be a good beginning. For example, here you have an example of probabilistic multitemporal corridor, okay, which combines multiple corridors in a single probability surface. And here, this is a reconstruction of the Silk Route made at 60 meters per cell, which was very costly. And this is what happens when you do it for the whole of the year. I mean, you put all the factors and you don't take into account temporality. So from Istanbul, it's much better to go through the plains, the northern plains, to reach Xi'an than the classical Silk Route. And but if this is true for the whole of the year, but if you actually do this in summer, the route adapts remarkably to what we know from the Silk Route and explains lots of stuff like the distribution of Indus cities. And this is the Himalaya Pass, and this is Lhasa. And here is the city of Lhasa, which was a very important commercial center that was commercing with the Silk Route related material. So, you know, I mean, it's you just not have the higher probability. but in the 10th percentile, which is not such a big deviation, you have parallel routes that explain the distribution of sites, which is so. I mean, this type of analysis allow us to say, okay, the silk route had to be, the final configuration of the silk route was probably related to the need to transport stuff during the whole of the year and not just at specific seasons. So obviously, when you have something like this, you can move into network analysis and include other things like speed, type of transport, change of type of transport, and you can start analyzing distribution of imports or material. So, so I mean, this is for one of the, this, as you see, there's lots of new approaches to movement. But now we move to advanced remote sensing technologies, okay? Also, in this case, multi-temporal data are having a big impact on also multi-source data fusion, not just one sensor, but the combination of several with the statistical approaches for this combination. I mean, of course, these analyses now are not just reduced to remote sensing or photo interpretation, but they include lots of types of data, which are like 3D data or vector data that are usually associated with other type of approaches, not remote sensing, but GIS, okay? And of course, we are not reduced anymore to use vegetation indexes or moisture indexes or just photo interpretation. We are starting to develop our own algorithms for the treatment of particular types of data. I'll put some examples here. This is while I was in Cambridge, one of my tasks was to reconstruct the Paleo River network of the Indus civilization. So for this, we use, as you can see here, lots of different types of data and thousands of images put together, combined, that allowed us to, with different techniques that allowed us to reconstruct the Paleo River network in very different environmental conditions. Those yellow here, this yellow color here, are dunes. So imagine up to what extent we were able to, those are agricultural areas in the top. I mean, some examples of Paleo Rivers, but we realized that our network was not complete. So we developed what we call a multi-scale relief model using tandem mixed data, which is excellent. If you have a chance to use it, it's really cool. And basically, this what it does is to create a micro relief, which is independent of the size of the feature you want to detect. So you have several examples of other microtopographic reliefs, visualization methods. And here the letter G is the MSRM. As you can see, it shows the Paleo River continuously, not just only fragments, okay? So this is a combination of both methods, and you can see some Paleo Rivers are only visible in one of those, okay? So the combination of these sources, it's essential. And actually the MSRM is a more typical GIS type of analysis, but of course it's not implemented in GIS because it's very costly. It's implemented using cloud computing because it's computationally very heavy. So we are also developing lots of new approaches to the detection of archaeological sites. In this case, it's combining Sentinel-1, which is a multi-band, multispectral satellite, and then a synthetic aperture radar, which is Sentinel-1. Okay, and this is the combination, the RGB bands, the red, near infrared, the shortwave bands, and then the synthetic aperture radars that I treated to obtain as much information as possible. You have here, yes, as you can see, it's lots of images with some data cleaning, and then these images were used to train a machine learning classifier, in this case, a random forest pixel-based. Okay, and this is the result we obtained. This is in India, in the Cholistan Desert. And those are the different types of sites. This is a bit slow, so I'm going to move it forward. As you can see, I mean, there are several sites that look like the Rebel Alliance symbol, which is very puzzling. But yeah, I don't know why. I mean, I think it's because of the dunes. Anyway, so yeah, those are the results of. As you can see, there are several bands, like for example, the B5, B4, B2, B12, and in general all those of the synthetic aperture radar that are very distinctive for archaeological sites in red here. And you can see that in the linear discriminant analysis, the sites are in purple. So yeah, we detected lots of new sites, some of them huge, which is very important because in the Indus, most sites seem to be small and there's only 5 cities known. So there are now 4 big sites now more. And yeah, those are the results and the distribution of sites. But we realized these sites were only visible in a certain area. Okay, in fact, very few of them were detected in irrigated areas because probably they have been flattened out. And whenever you have the deep dunes, they are not visible either. So this is telling us there's lots of sites there under the dunes. And the expansion of the desert probably was one of the causes of the fall or disintegration of the Indus civilization. So we detected lots of sites. We had 100% success with the ones we knew, and we use as test data. But this is not applicable to other areas. So we move forward to create a new type of algorithm, which combines new data like thermal data, pulsar, and some derived products. That is, we didn't use just raw data, but we started developing our specific types of data focused on the detection of, specifically developed for the detection of sites. Okay, so we tested that in a very big area with including different environments just to see how this works. And you can see the thousands, well, you probably cannot see it. I'm going to zoom in. So all these white dots are sites. You see some examples here. I'm zooming a bit more. So you see this one is this one. It's really cool. This one is one. And it's very funny because what it's detecting is the lower area. So the algorithm is distinguishing modern habitation and eliminating it. You see? All the area, it's this white area, it's this area here. So wherever you have modern habitation, it just eliminates it, doesn't take it into account. And also sites that are not visible, that are only visible with a treatment of the raw data, you see? So these are, I didn't count it, but the preliminary analysis shows more than 15,000 sites in this area. So, but what about these sites that are not visible anymore? As some of you might know, we have been developing some automated approaches. Now, this is a bit in the past. Now we are moving to robots in the field. But yeah, the idea is the same. You just obtain lots of images. We are not using photogrammetry for this, but SLAM to create the orthomosaic, and we apply different types of algorithms. We are now moving from, this is a random forest, pixel-based classification, and this is a mask RCNN. This is an object-based classification, which seems to work better, defines much better the pottery. And, you know, these are comparisons between traditional survey and this automated kind of survey. And you can also filter vegetation. So you can correct statistically the distribution. You can obtain lots of new information like how pointy the pottery are, which is telling you if the pots have been in the surface and move a lot or not, how big they are. That will tell you also if the site is in danger or not. For example, in this site here, there's a small elevation here, which we can extract this information also. And now Garcia Molsosa will be presenting at CIA an application of this a much larger scale in Africa. And it's pretty interesting if you are going to be there. But what happens, you have the tumuli here, the line, you see the lining of the plug here, it's going this direction, so it passes, it distributes this way, and then in the corner of the field, it moves down. So you can even study how the distribution was created. In fact, all this distribution comes from here, because in here we have the larger potsers and the pointier ones. So this means that the site is still being affected by surface activities. Okay, this allows you also to differentiate between type of sites. Now we are moving to try to identify specific pottery, but this is going to take a while because the camera we are using is very expensive and nobody wants to put it in a drone. So you never know what could happen. So yeah, with this kind of approaches, you can survey, you can obtain very visual information of the distribution of pottery over a large landscape. And, and then go focusing on these sites and try to extract information you cannot get from the drone. So we move now to the recording of analysis of 3D items or events that was also a characteristic of all GIS approaches. But now we have new types and increased accuracy of 3D data collection methods. We are moving from classical 3D recording to analysis. I mean, this is very important because up to now, most 3D were recording and displaying and playing, and very few analysis. And there's an important public use and involvement and teaching and accessibility issues involved with the 3D data that needs to be explored. So, I mean, those are classical examples of, for example, simulation of a flooding event in using LiDAR data. But LiDAR data can be used also for the automated detection of mounts. I mean, this is something you need to be aware. These automated detections, you need lots of information to see up to what extreme they are useful. You need to look very well because some of these approaches, they detect more sites they knew, but they are detecting 200,000 sites more. Okay, in this case, we were very careful and we combined deep learning, CNN-based approaches, object, and machine learning. So those are two machine learnings complementing each other, and we reduce a lot the presence of false positives, making this data set probably the first useful data set for archaeological survey for a very, very large area, actually. Almost 10,000 tumuli detected in 7% of the surface of Spain. Those are the false positives, yeah. Obviously, you can use 3D data also for excavation analysis, and we have seen an excellent, truly incredible example today. In this case, we extract automatically the stratigraphy of the site. Okay, and you can also 3D data today can allow you to go beyond what humans can do. For example, this is a process. This is a project which I'm directing together with Alexandra Libarda. It's some of you will know. By the way, she gave me greetings for Marcos. And I mean, we are scanning sheets at very, very high resolution. We treat the models. First, we simplify them, we orient them, and then we merge them. And what we have realized with this project is that we can, there's very little variability between scans of the same sheet, which proves that the scans are good. Okay, there's much more variability between classes, that is, sheets with the same regime. For example, we are talking about one land race, one type of sheet, okay, in this case. So between them, if they have been subjected to the same growth conditions in terms of manure and access to water, they have some variability between them, but nothing compared to the differences between sheets with different agricultural regimes. So we cannot just identify different species. We can differentiate. We can also differentiate clearly between different land races of the same species. And we think we will be able to differentiate the growth regimes of the different species. That we will be able, if we manage this, we will be able to create a unique tool for the analysis of agricultural and climate events. I mean, this is the method we use to now we are moving to CNN. Please, I'm finishing my time, so I will not bother much with this. Then we can also use machine learning for the extraction of information. In this case, we use the survey of Indian maps. At the moment, we have georeference almost 1,000, but we developed this system that, the maps were very different. So we had to create a specific curriculum learning approach, and we were able to extract 6,000 sites out of these maps. As you can see, there are some lines because we still lack some maps in these areas. Okay. And okay, this we are also trying to implement in terms of phytolith detection, hopefully in the future pollen. The phytoliths are actually, I mean, it's very efficient because you can measure things that are very difficult to measure with a microscope. So it works very well for the automated detection and classification of phytolith. Obviously, with all these sites you are detected, you have huge data sets of sites that cannot be managed using traditional methods. Imagine an euphoria multiplying by 10 the number of sites they have to take care of. So we also thought it important to develop methods to analyze, to manage and monitor these sites. For example, in this case, these sites we detected in the Kholistan deserts, we have realized that they are under threat by agricultural expansion. So this method, it's able to automatically detect any agricultural expansion affecting a site and send an email or a message to the person in charge and explaining how this site is being affected. Okay, have some statistics. As you see, it's a disaster in this area. They are losing lots of sites. Also, I mean, I'm not going to go into the detail of how we develop this, but we use a combination of radar and some topographic analysis to eliminate false data. A series of bands to actually reconstruct agricultural expansion during the last 50 years, urban expansion during the last 50 years, which tells this can detect individual buildings on a weekly basis. So it's a very important tool to protect sites out of urban expansion, which is very important in India. So as a conclusion, I can say that geospatial approaches to archaeology have the potential to automatize simple repetitive tasks and generate big data that can be employed to approach complex archaeological questions. Okay, they can also analyze data that are not visible or not apparent to human senses, improve analytical capabilities in most areas of the field, and open new avenues for public engagement, dissemination, etc. However, these methods are not anymore out-of-the-box solutions. They need to be designed specifically for your own research question. They combine different sources at different periods with different tools. So specific projects need specific approaches. It's clear there's a blurring of previous software subdisciplines. I mean, it's difficult to talk about GIS today, but geospatial perhaps, or GIScience. There's a pressing need to start training multidisciplinary researchers in different subfields. The age of the JV, GIS technician, topographer, air assessor, my work doesn't work, please could you come and have a look, should be at an end. So thank you very much for listening to this 3 minutes over long talk. And yeah, I guess we can discuss, have some questions at a later stage. Thank you.
Thank you, Hector, for this